Okay, so I'm back with some more information about these unique angles, which I briefly went into in my last video on the topic. So, to give a little bit of backstory, just in case you haven't seen that, essentially I worked on a problem around about 1.5 to 2 years ago that was about integer points on a two-dimensional plane. The idea is if you have an analog stick and you move that analog stick, it moves to a specific coordinate. And my question I wanted to answer was, how many unique angles are there? So a unique angle is an angle from the origin, or 0, 0, to a point. Here I've represented it as AB. Now I'm going to read most of the stuff I've written here, but I will elaborate on most of the stuff as we go on. So a unique angle is an angle made by a line from 0, 0, which is the origin, to a point on the plane AB, such that the line has a gradient of b divided by a, and that fraction is irreducible. So what that means is that if that fraction, b on a, can be simplified, then that angle is not unique. So an example of a unique angle is 1, 1. 1, 1 has a gradient of 1 because it's 1 divided by 1, which is rise divided by run. It's just the gradient. Whereas if you keep going along that 45-degree angle line, you have 2, 2, 3, 3, 4, 4, and all of those can reduce down to 1, 1. So here I've just written a little bit of mathematics. I've said that, note that the point 0, 0 is a unique angle, that no other point p in Zn, which is the n-dimensional integer set, can produce the same properties. So essentially I'm saying that the origin has properties, the point on that origin. So a line from 0, 0 to 0, 0 is a line with 0 length, and no other point from 0, 0 to whatever point can produce that magnitude. Also, because it is a zero-dimensional line for any n-dimensional 0 point, which I've written here as p. So I've written here, if I just point out with my mouse, p equals, this bold 0 represents the n-dimensional 0 point, which is, 0, 0, 0, whatever. So what it means is that if you take from 0, 0, 0 to the 1, 1, 1, 1 dimension point, it'll have some length. For example, here from 0, 0 to AB, this line has a magnitude, a length. But if we make this AB 0, then the length will be equal to 0. Now, this line also has an angle theta, and one other property would be that the 0 angle from 0 to 0, the angle doesn't really exist. It's a little bit complicated, and I'm not really going to go into it, but it produces some interesting properties that no other line has. So, for the sake of this argument, I've said that the 0 point, the origin, produces a unique angle, because indeed it is unique. So going on, I've written that an example point that does not produce a unique angle would be the point 4, 2. So looking at that gradient, you have 2 on 4, which can be reduced down to 1 on 2. Thus, the point 4, 2 is not a point that constructs a unique angle. But as you can tell, the point 2, 1, which has the gradient 1/2, is a point that constructs a unique angle due to the fact that 1 divided by 2 is irreducible. And here I've got a example. So we have the point 4, 2 and 2, 1. So as you can see, 2, 1 lies on this line from the origin to 4, 2. So naturally that means anything above this point is not going to be a unique angle. So this is the minimum point. It is the only point. So what you can do is you can look at these grid lines. Now for this image you can't actually see the values on the XY axis, but there is a this is 2 here and 1 might be here. So as you can see, 1 doesn't lie on one of these corner pieces. So this means that this point here is not an integer point, so it's not a point we care about. So this is the minimum integer point. So everything after it is not a unique angle. So from here on out, things are going to get a little bit more complicated. We're going to get into some mathematics. I'm not going to get too deep into it. Just a little note that my presentation skills aren't exactly neat. It's not very good. I'm not good at presenting information, so I really hope I present this in a very informative and understanding way. So I've written here, what makes this interesting is that if you look at the number of unique angles from 00 to nn, which is a square, as n increases, the number of new unique angles varies. So that means if I look at the square from 00 to 33, so if we look here, this is a rectangle of 4, 2. So what we're looking at is all the integer points within here. So here we're actually caring about perfect squares, not rectangular regions. So if we look at the points from n equals 1 to n equals 100, I've written out the 100 unique angles for each square. So the first square from 00 to 11, and underneath here I've got the number of the values of the differences between each of those values. Now, the reason I've written this out is because I want to elaborate just how variant these unique angles are. They aren't something that is, I guess, predictable. So as you can see, we have 3. So this is the number, the new number of unique angles between 11 to 22. So if you take all the unique angles from 00 to 11, and you take all the unique angles from 00 to 22, the new number of unique angles is 3. And then as you increase n, it becomes 2, 4, 4, 8, 4, 12, 8, 12, so on and so forth. And it seems to create this random pattern of higher and lower numbers as it goes on. And you can't actually mathematically predict any further numbers. So beyond this, which I believe is the difference between the 99th and the 100th, you can't write a formula for this series due to, as it says here, as you can see, the number of unique angles between iterations of n seems random, but why? The simple answer is because it has to do with the distribution of prime numbers. Because we cannot describe mathematically the distribution of prime numbers, we cannot represent the series above as a sequence, and thus we cannot calculate easily the number of unique angles for any n by n square, and also any region on any dimension plane. And we will get into why that is in a couple of slides from here. So this is just another interesting point where I've said that below we have 2 plots for all the unique angles, which are red, and non-unique angles, which are black, for the plots from 00 to 33 and from 00 to 44. And for any n by n and n plus 1 by n plus 1 region, the number of new points is equal to 2 times n plus 1 plus 1. And what determines if any of them are unique lies solely on whether or not another pre-existing point lies on a line from it to 00, which we said here. We said that because this point creates a line that goes through another integer point, this point isn't unique. So yeah, that's just a little thing I wanted to point out. So this is about where the mathematics starts and where I somewhat begin to describe how exactly this works. So to determine if any angle is unique, we need to determine if it is reducible. The gradient is what I'm referring to here. So formally, for a point AB, we can say that B prime over A prime, that's the dash. I've been taught to refer to that value, that symbol as prime. We say that B prime on A prime is equal to the fraction B divided by the greatest common denominator AB of A and B divided by the fraction of A divided by the greatest common denominator of A and B. Again, so what this means is that if either A or B share a common factor with one another, the fraction B prime over A prime will be reducible. Thus, if either A, being the non-reduced form of A prime, so if A is greater than A prime or B is greater than B prime, then the point AB is not unique. So just to go in, an example would be if you take the 0.44, let's take the 0.24, then the gradient would be 4 over 2. Now that would be the b and the a. B would be 4 and a would be 2. But b prime in this example, because they both have a common factor of 2, it would reduce down to 2, 1. So b prime would equal 2 and a prime would equal 1. So here we would say that a, which is 2 and a prime is 1, so 2 is greater than 1, or b being 4 and b prime being 2, so 4 is greater than 2. And that means that the fraction is reducible, thus not being a unique angle. So this can even more simply be represented as if the absolute value of the greatest common denominator of a and b is equal to 1, then a and b is unique. And this is solely for the fact that a and b can be both negative and positive. So if you have negative 1, 2 as your points, then your greatest common denominator would be negative 1, thus making it unique. So this is where I've given a little understanding for those of you who don't know sigma notation. To find the sum of numbers s equals 1 plus 2 plus 3 all the way up to the number n, we say that s is equal to this crazy notation here. And to break it down, this symbol here is called sigma, or capital sigma, the Greek letter. And we say it goes from 1, so I equals 1, and we represent I here. So we say from 1 to n. And then we represent our formula. So here we're just caring about these integers 1, 2, 3, 4. So we just have the I. And then with each representation, it goes I equals 1 plus I equals 2 plus all the way up to n. And then here I've written out a formula for calculating the unique angles for two-dimensional space for a and b greater than 0. That's an important fact. If you have a and b in both positive and negative, then things become a little bit more complicated, and I really didn't want to write that out because it becomes a nightmare for me to explain. So this is kind of complicated as it is, so I decided to stick to the positives. So the total number of unique angles from 0, 0 to AB, where A and B are positive, is equal to 3 plus the double sum. So this is where I said things get a little complicated. You're doing a sum for a sum. It's really interesting stuff. And then I'm not going to explain how this sort of thing works, but then we do it for this little variable here, and I've defined that this variable is equal to either 1 or 0, depending on whether the greatest common denominator, the absolute value, is equal to 1 or not. And really the absolute value doesn't matter because we're only dealing with a and b being greater than 0, so this cannot be anything other than 1 or negative 1. And the reason we add 3 here is because rather than starting m or n at 0, we ignore that because we know the only unique angles on the axis are 0, 1, and 1, 0, and of course there's the origin, so those are the 3 points we're adding onto this total sum. Now, before, when I was talking about the prime numbers and how they cannot be written as a mathematical sequence, this is the reason why. The greatest common denominator is used in this example because of the fact that we cannot represent prime numbers in a formulative sense. You can't just plug a value into a formula and find, say, the nth prime. We can't just say, what is the 1026th prime number, plug it into a formula and find a solution, or at least not easily. There are ways to do it, but it's not simple to do. So I've written that this function relies on the greatest common denominator. This is because if a and b are co-prime, this point produces a unique angle, and coprime simply means that the greatest common denominator is equal to 1. This has a lot to do with prime number theory, and due to the mathematical limitations, a better formula or function does not exist. And that is mostly true. There are other ways to represent this function, but it's not as nice. This is the cleanest and most simplest way to get the thing to work, and honestly, this is how I used in my last video. My program pretty much does it this way. And when I worked with the negatives, so as you could see here, we had from 1, 1 to the positive a and b. So these are never negative. And then if I did deal with the negatives, I had another set. It would be 3 plus the positive series, and then I do plus the negative series, and that's more or less how it works. So here I've done a example of a 3-dimensional space just to show that this works very simply for any dimension. Note that this function was for 2 dimensions. Any dimension is fairly simple to do or represent. So for 3 dimensions, it would be as followed. We'd have, instead of 3, we'd have 4 plus a triple sum this time of a new variable where we have 3 degrees. It's 3 dimensions, 1 dimension, 1 variable for each dimension. And then we'd have it for the greatest common denominator of each of those variables. It's very simple to change. And I've added a little side note here where it says we add 4, this 4 here, because we account for the 4 non-negative integer unique points on the axis. In general, for only positive points a, b, or it's not just a, b for 3 dimensions, it would be a, b, c. For any positive integer point, it is the number of dimensions plus 1, and that plus 1 is the origin. But if we include the negative integers as well, we do 2 times the dimension plus 1. So if we wanted to include the negatives here, we'd not only have a negative sum off to the side here, but this 3 would become 5, because remember, if it's non-negative, it is the number of dimensions, which is 2, which is represented by the number of sigma notations, plus 1, which is 3. But if it's including negatives, it's 2 times the number of dimensions plus 1, which there's 2 here, so we'd say it's 4 plus 1, which is thus 5. So that's pretty much it. That's more or less exactly how the number of unique angles work, which gives you the number of unique angles within a region. And this is as simple as I could write it and explain it without going into some of the more multi-dimensional stuff or the negative variables. It's essentially the same thing, just with a little bit extra math. But yeah, I hope this was a little bit interesting. I'm not the best at explaining, and I kind of rambled on for a bit, but I hope this makes sense and you guys find this interesting. I will provide this Microsoft PowerPoint documentation in the description. I'll be sure to fix any errors in this before I upload it. But yeah, thank you for watching, and I hope you find this kind of thing interesting. If this is something you enjoy, I'm more than happy to go into more similar things in the future.